So I'm going to, so just a little bit of context. So I'm a professor of biostatistics at the University of Oxford, and that means I kind of carry two hats. I carry a hat in the Department of Statistics, where I research in Bayesian methods, really, Bayesian methodology for high-dimensional inference problems. And also I have a joint appointment in the Nuffield Department of Medicine in the Wellcome Trust Center for Human Genetics, where we spend a lot of time working on focused research projects, trying to understand something about the genetic contribution to human disease and disease risk. And so in this context, kind of increasingly over the last, I guess, 5 or so years, I've become interested in kind of robust, what I'm going to hopefully express across to you about something called robust inference. Okay, and I was chatting to somebody who was kind enough to walk me from the hotel to the university here this morning, and I was explaining that one of the things that we do when we work on genetic association studies, so here we're interested in, say, the effect or the disease risk implied by carrying a particular genetic variation at a particular point in the human genome. And so we set up a study, we gather some data. This could be very high-dimensional data. We start modeling it statistically or with a machine learning approach, and we find associations. And then the next thing we do, and perhaps the most important things we do, is we try and break them. Yeah? And it's a really good kind of thing. The first thing you should do is try and bust your results. Yeah? Really try and break them from any which way you can. Yeah? And unfortunately, what you find is that the really interesting stuff normally just falls away, yeah? Because of artifacts that have arisen in the data. It's a kind of too good to be true. And what's left is the stuff that validates, the stuff that is true kind of signals of nature, yeah? And so that's informally, I guess, what I mean by robust inference is that we really want to be careful and scientific, yeah, about our approach to, say, reporting associations or reporting error rates from predictions. And I think this has an impact on not only on statistics, but also on machine learning, as maybe you'll agree with me by the end of today. Okay, so what I'm going to talk about in the next kind of 2 lectures is really just to give you a flavor of a formal approach. How do we formally approach robust inference? And, first of all, what do I mean by robust inference? Why do I think it's increasingly important, both for statisticians, well, we're all kind of one group, yes? There's statisticians and machine learners. I'm going to focus very much on my own kind of particular area, which is Bayesian approaches to robust analysis. I think there's some particular issues that arise when you're adopting a Bayesian or a probabilistic approach to modeling, and why you need to be especially sensitive to issues of assumptions when you're adopting Bayesian models. But be aware, and I'll point you to the literature, that there's a really kind of a vast body of work in non-Bayesian approaches like estimating equations and robust statistics from a classical perspective. I'm then going to take you through a kind of a series of kind of, I guess, increasingly complex scenarios. So to start with, just talking about likelihood functions or building probability models which are not prone to kind of track unusual events. Okay. So what you might worry about is that we call them outliers in statistics. If you have one unusual person in your, suppose you're trying to build some machine learning system about, using a data set from people collected in this room, and then there's one person in there that just has really atypical behavior. Yeah. Now, we know that certain models, especially if you're building probability models, can just track that one individual. Yeah. We call it high leverage. Okay. So I'm going to introduce the idea of trying to build probability models which are less sensitive in the tails, we say. So are less likely to go off sniffing around and following one individual. They'll try and stay where the main bulk of the data is. So I'll discuss those kind of robust, and I'll introduce the term, which is kind of slightly unusual, but you can think about it, is that in a Bayesian framework, being outlier prone is a good thing. Yeah, so you've done a class on Bayesian statistics, I think, this week, or you've certainly done probability model. So even though it's like 9:15 on a Sunday morning, you kind of think of why is outlier prone a really good feature of a Bayesian model. Okay. Of course, the kind of two central ingredients to building a probability model, a joint probability model in Bayesian statistics, is to factorize the joint distribution in terms of a likelihood. Formally, it's a sampling distribution. I'll be precise in what I mean by that statement. And of course, there's this prior, this kind of mystical object that sits there. And I guess most of the work in robust Bayesian analysis has concerned itself with specifications of the prior. Where does the prior, when you start off in Bayesian statistics, it's always, the kind of, where does the prior come from? How can you believe that? And so naturally, there's been a lot of research, formal methods, in trying to look at how do we assess sensitivity to prior assumptions. Okay. And then finally, and I think I'll cover this will be covered in the next lecture, there's been some recent very interesting work in the robust control literature and in econometrics about building formal methods of quantifying robustness using information kind of geometry. So building Kullback-Leibler balls around your model. Yeah? So I have a machine learning model. It's a probability model, so we can think of that as a point in the space of all distributions. Okay? You have your model, and then what I'm going to do is I'm going to construct a neighborhood around that model. Yeah? A space of similar models. Yeah? And we're going to have to define what similarity means, and I'm going to persuade you that the Kullback-Leibler is the only coherent way of defining what it means to be a local model. And then we're going to explore what happens to your conclusions within that neighborhood. Yeah? So you imagine, you've spent PhDs building this machine learning model, or working on machine learning models, and then I say to you, oh goodness, if you tweak that model a little bit within this neighborhood, everything changes. Okay. So this is really, the final bit is about how can we do formal sensitivity analysis in a very kind of rigorous way, looking at Kullback-Leibler measures and something called local minimax actions. Okay, so a few slides of really just to kind of get us thinking about what is this. Okay, well, clearly, yeah, in order to learn something, you have to assume something. Okay, so all of statistics and of course all of machine learning is based on assumptions. Okay, as quoted from famous statistician Shakespeare from King Lear, nothing will come from nothing. Yeah, we have to make assumptions in order to learn. Okay, so for example, and of particular interest here throughout this talk is the use of Bayesian probability model or machine learning approaches. So underlying the Bayesian probability model is, of course, an explicit joint probability distribution, okay, which I'm going to call the model, which is a likelihood function. Strictly speaking, it's not a likelihood function. It actually has to be a full sampling distribution. Okay. So when Fisher, who really kind of devised the notion of likelihood, when he talked about likelihood, it was in the context of likelihood ratios. Yeah, so what's the plausibility of a particular parameter set in theta over a different setting of it, theta prime? And you define that ratio of the likelihood of theta over the likelihood of theta prime, or the log likelihood ratio, the difference of the logs, as just the ratio of the probabilities. But what it means is that classically you don't have to be a full normalized joint probability. But if you're Bayesian, you need a sampling distribution. Yeah? You've covered Bayesian statistics this week, I hope. Otherwise, we're in for a long, long morning. So Bayesian statistics is generative, yeah? Which means that you, in some sense, it's a really nice way of thinking about it. You have to be able to generate samples, yeah? Be able to simulate samples under your probability model. Okay, so if you're Bayesian, there are kind of two ingredients typically. There's the sampling distribution, the probability of the data given a setting of your parameters, theta. Theta here is going to soak up everything. It's going to index the model, or perhaps a space of models. It's going to index the parameters within the model space. Okay. And x is going to denote all the information that you have, data. Okay. And so we have, if you're Bayesian, you've got the likelihood, probability of the data, or the sampling distribution, probability of the data given the model, and the prior probability of the model. And just to note rather loosely, you know, unless clarity kind of dictates, I'm going to, rather annoyingly for you, I'm going to interchangeably use, actually I won't use PR much, but I use little p, theta, and pi p theta to represent either distributions or densities or mass functions. Yeah? But the context should be very clear when one is a distribution and one is a density or vice versa. Okay. So all of these things are based on assumptions. What do I mean? You know, we're going to start to try and get into like what do I mean by formal definition of robust? Like robust to what? And I mean robust in terms of assumptions. And the concept is fairly vague, but you know, I would really state statements, yeah, which you will hear typically in the abstract or the introduction of a model, of a description of the model, which is, oh, let's assume that the data is normally distributed. Or, you know, assuming conditional on the model that the data is IID, or the process is stationary, or I've put down a Bayesian prior. Or, and this is, I think, again, particularly kind of important and increasingly important, oh, I'm assuming that my training data matches the environment of which I'm going to be applying the model. Okay. And in this kind of ever-changing kind of world of big data, as populations change and data capture methods change, this is kind of, this assumption is becoming kind of increasingly important. Yeah. So we know, like in statistics and statistical genetics, problems about ascertainment bias. You go out, you gather a training data, you build a model, it looks fantastic on it, you go out into the real world, you apply the model, and the error rates are much bigger than what you had expected when you actually kind of built the thing. And the reason is that the data, the population of data that you generated, you sampled from to get your training data is different from where the model is being extrapolated to. And so by robust, we're just going to mean, so there's a good book by Huber here on insensitivity to small deviations from the assumptions. Namely, if the data isn't really normal, but it's close to being normal, yeah? Or if there's still some dependent structure in there other than IID, yeah? Then we wouldn't want our model to be brittle. Yeah? We wouldn't want the answers or the conclusions to change dramatically. So in statistics, the word robust was really kind of coined by Box in '53 when he was looking at, you know, the effect of Gaussianity. We know one of the problems of using the normal or the Gaussian distribution has very light tails. The tails obviously decay quadratically in the exponent. The other kind of important thing is when we talk about robustness, we really want to be contextual. We want to be thinking about what do we mean, robust towards what? Yeah, is it robust towards, if you're interested in just making prediction, then you want to be able to make robust, obviously, predictions. If we're interested in looking for, say, you know, does this drug improve the treatment effect on this patient, then that's the primary question of interest. And so it's important to say that because it's no good just saying, oh, the student distribution, for example, is robust. That doesn't really make sense. Yeah, it's robust with respect to what? So we know the student distribution is robust in terms of the central location. But it's not robust. It loses power when the data is non-Gaussian if you're doing a t-test. Okay. And so a little bit of a side here is that I'm not sure if you've done any decision theory, but it's my belief that decision theory is the kind of the appropriate framework to kind of analyze robust issues. You know, lay down, make explicit, what are you trying to do with the model? Yeah? What is the primary source or the answer that you're trying to achieve? And then frame robustness around that. Okay, so robustness, of course, is a property that everybody should seek out. I mean, it's a bit of a vacuous kind of, nobody's going to say, if I asked you, if you came to me and said, oh, Chris, I built this model, it looks great. Say, is it robust? You're not going to say, well, no, it's brittle. Yeah? So, it's a bit vacuous, but, who would actively choose non-robustness? But it's a property I think we should be aware of. It's really about kind of formally kind of thinking about assumptions that go into models. And so in the words of kind of Jay Cadane, robustness is a fundamental issue for all statistical analysis, and said, in fact, it could be argued that robustness is the subject of statistics. And it kind of aligns well with this notion of statistics as kind of, you can think of it as being precision in precision. Yeah? What we worry about is being precise about what we don't know. Yeah, that's the kind of fundamental thing of statistics, is about working with units of uncertainty. And I guess in machine learning as well, yeah? A lot of things, your units are units of uncertainty, what we don't know. We're trying to learn something. Yeah? So we start off from a state of, from some state of knowledge, and we're trying to improve our knowledge about something. Yeah, we're trying to learn. And what we want to do is be precise about how much learning we've done along the way. Okay, and of course, good statistical practice, as I said, we try and break all of the results that we find. We'll try and use every available method, diagnostic plots, graphical visualization, shake your data, bootstrap the data, subsample the data, all of these things to try and, shake it up and just see if the thing remains stable. Make sure that the conclusions that you arise at are not sensitive. Okay. So in what follows, what we'll see is that there's always this kind of trade-off that goes on in statistics and in machine learning about choosing one method or, say, choosing a particular approach over another. Yeah? So, things that enter into that might be, whether it has to be secure. Yeah. So, does the data analysis, is there a privacy issue with the data? That will kind of lead you to choose one particular algorithm, say, over another. What's the training time? Yeah. If you're working in statistical genetics, we can afford to run, we can afford to run models for hours typically. If a patient comes into the clinic, I sequence, say, their cancer, some cancerous tissue. Yeah, we don't need it's not like a recommendation system. We don't need an instant response. We can wait for a few hours to run a statistical model. And all of these things kind of enter into our kind of choice of the algorithms that we're going to apply. Yeah, they'll often involve trade-offs. Yeah, if I give you a constraint in how much runtime that you have, that will constrain the type of methods that you've got. You'll choose one method over another. And robustness is a similar kind of ingredient into this space. So you can think of robustness as kind of trading off. It's like an I quite like this quote. It's a bit like an insurance policy. Yeah, you're trading off a little bit of efficiency. Yeah, so you have a model that said, suppose the data is really Gaussian, normally distributed, then I fit a normal model, or I fit a particular model to that. And that's the most efficient thing statistically. That's the most efficient learning mechanism that you could apply. Yeah. But by robustness, I mean you'll use a slightly less efficient model. Yeah, it won't learn at the same rate, but it'll protect itself against deviations from the assumptions. And so that's what I mean by robustness. It's really a trade-off. Hopefully you only lose a little bit of efficiency versus the original model if the original model assumptions are true. Yeah, but you protect yourself against large kind of misjudgments if the original model is false. So the historical context in statistics, most of statistics is about trying to estimate central locations, means of averages of wheat yields and disease and things. Yeah? And of course, the normal distribution or the Gaussian distribution really kind of dominated dominated this field. But even, you know, in applied statistics, people understood the danger of just assuming normal errors. Okay, so people like Newcomb and Bessel noticed that actually in practice, when they came to gather real data, yeah, that kind of the classical bell-shaped curve of the Gaussian was often not met. So kind of here's a quote from Newcomb in 1886, who says, as a matter of fact, you know, the cases where the errors are really found to be normal, you know, it's quite exceptional, you know, to really come across a data set that truly follows the kind of normal distribution. And the general rule, he says, is about 1% of the things tend to have much kind of heavier kind of outline or tails. Or there's this other quote, so this is quite nice. It actually, so says this way of like, you know, if I asked you to estimate the average, you know, heights of schoolboys, yeah, most people would just take the, you know, the arithmetic mean. Okay. Now we know that that's the most kind of efficient estimator. Yeah, under the assumption that all of your data really comes from that population that you're trying to estimate. But we also know that the arithmetic mean, if there's contamination in the data, will track it, yeah, because it gives kind of equal leverage to every point. And so there's these so-called robust estimators, like the median. That's robust. You just take the middle point. So it doesn't matter if I go to the middle of, if I take all of your heights here and I go to the middle, it doesn't matter if I start to introduce some like NBA basketball stars, yeah, through here. The middle point, of course, won't change. Your middle height will, but it's where your mean height will start to kind of track upwards, yeah. And so one way you can, rather than just taking the median, one thing you can do is called the alpha trim means, which is you chop off the highest alpha and the lowest alpha % of your data, and then estimate the average from the remaining bulk of the data. And it's kind of interesting that the French farmers were doing this in like 1821. So here's a quote from there. It says, like in provinces in France, when in order to determine the average yield of an estate over a 20-year period, what they would do is remove the largest observation and remove the smallest observation, and then take the average from those remaining 18 points. Now, we know statistically that that's not the most efficient thing to do, yeah, if the data always really comes from the population. But the idea is that there are exceptions that would arise, and we should kind of make allowances to them. Okay, some other kind of approaches I'll kind of skip over, but again, you know, these slides will be online, so for your kind of reading, you know, there's this big debate about how should you measure scale, yeah? Whether you should use the standard deviation, the square root of the sum of squares, or whether you should just take things like the average absolute difference. Okay. And so there was a big kind of debate about this. People use robust, and then Fisher kind of showed that you lose efficiency with this estimator. And then everybody kind of switched to using standard deviation until Tukey came back and said, well, okay, yeah, you lose efficiency, but only under the assumption that the model is true. Yeah? And if there's a contamination event as low as 0.002, yeah, so 0.2%, yeah, then actually this is no longer efficient to use the standard deviation. You're better off using a robust estimator. Okay. So Huber is really one of these names that kind of dominated the field in terms of classical approaches to robustness. As I said, I don't really, you know, have time to do justice or to go into this. I'm just, you know, I put some references up, and there's references at the back of the slide to follow up on robust inference. Okay. But I guess it's kind of things about, we think about efficiency relative to the ideal model and what's lost. Yeah, so how much are you trading off in terms of your insurance policy in taking a robust model? We think about stability. You know, if my assumptions of my ideal model are perturbed slightly, what happens to the kind of the new model? And then we think about breakdown points. You know, if everything goes completely wrong, you know, you don't want the model to kind of completely collapse on you. Graceful degradation, I think it used to be called in machine learning. Okay, so what are we going to cover? we're not going to spend much time on the classical approach of Huber. So I'm not going to cover things like M-estimators, estimating equations, sandwich estimators, leverage plots, and breakdown numbers. So these are all kind of important areas which I think, if you work in data analysis, you should be aware of these things. Yeah, I just like throw them out there and say, you should kind of follow these things up. I think they're especially important as data gets messy. Yeah, when data starts to get really messy and it's full of missing and outline observations. Yeah, these are kind of really useful techniques. What I'm going to focus on, because it's been the primary kind of area of my own research, is on robust Bayesian analysis. Okay, so we know that, and this, by this I mean probabilistic modeling. We're going to have, some sense, we're going to have a joint probability statement that we're going to make, or we're going to lay down about our data. So in one sense, if you're kind of a purist Bayes, yeah, you could argue, well, what is all this robustness? You don't need it, yeah? But, Bayesian approaches in one sense are inherently robust. Yeah, you don't condition on a single model. We're not trying to optimize, a set of parameters. Rather what you do in a Bayesian approach, again, it's this idea about you working in units of uncertainty. Yeah, as statisticians, machine learners, we work in units of uncertainty and learning about uncertainty through uncertainty. Yeah. So in a Bayesian framework, you don't condition on a single model or optimize or set a set of parameters. What you do is you formally quantify your initial state of uncertainty via a probability distribution. Okay. So you start off with a prior probability distribution that has support over all the possible things that nature could be. Yeah, all the possible models, the machine learning models that you might wish to adopt. And then you have a sampling distribution or likelihood function, which tells you is a forward generative process, tells me what's the probability of generating any particular data set that I might observe, if this was, given the setting of the model parameters. And so, that looks pretty robust. We're not kind of putting all our eggs in one basket. We're spreading out our probability measure over different models and different parameter settings. And then when you've done that, and, I presume you've covered this earlier, inference and prediction is typically made through posterior expectations. So we take, having learnt, all there is to know, P of theta given x, so this distribution here, in some sense, is a sufficient statistic for everything. What does that mean? It means formally you can throw away all your data. Yeah, if you're card carrying Bayesian, if you really believed, if you really were subjective Bayes, subjective Bayesian, what you would do is, having obtained this object here, that holds all the information for anything you want to do. You could discard your data. It's kind of formally, you can think of it as like a sufficient statistic. So under Bayesian position, there's no issue with model robustness. I've precisely specified my priors and my beliefs through this joint distribution on the data and the unknowns. And then I'm going to condition on the data, and then I'm going to live my life according to the Savage axioms, according to decision theory. So decision theory in Savage tells you, what to do with this object in order to proceed in a coherent and optimal way. Of course, this is totally kind of extreme. No one would actually kind of, well, hopefully, no one would proceed in this particular manner, because it assumes, in some sense, kind of infinite precision, subjective kind of precision. And we have, of course, the founders of Bayesian statistics, people like De Finetti and Savage, knew this. So, of course, here we have, like De Finetti. It's important to recognize that really we can only vaguely specify initial beliefs. And so, this is a quote again about robustness. It's important not only to know the answer that you got from your initial model, but what would happen if you change the model a little bit? Yeah, within the neighborhood of the initial assumed opinions. Do things change dramatically? If so, you've learned something. Okay. Savage as well, we talk about, this problem that the Bayesians have in specifying this object here, really, and then linking the likelihood in. I mean, really, the prior is specified relative to the likelihood. Yeah? They're intertwined. Yeah? So prior distributions can never be quantified exactly, and that's the difficulty, and that's the thing that kind of should worry you, I guess, from a formal perspective. So how do people deal with this? Well, the standard approach is to first of all begin with a working model. Yeah? So start with a working probability model for the data which you've specified to the best of your time and ability, and then investigate what happens around that. Yeah? If I perturb the model slightly, what happens? And we'll get on to talking about formal approaches to this problem later on in terms of defining this kind of neighborhood around the models. What does it mean to be local, and what does it mean to be perturbed? Yeah, and we're going to try and lay down some kind of rigorous foundations on that approach. So the idea goes back to Robbins and Good in the 50s. It's really just about good statistical approaches, good statistical analysis. What's interesting is that robustness, the kind of formal studying of robustness, was a really active research area in the 1990s and early kind of 2000s. In fact, it was one of the main research areas in Bayesian statistics. Okay. And it's not hard to see why, because at that point, people were continually being asked, well, what is this prior? Where does it come from? How can you believe the model? So there's a lot of work in there. And that work kind of tailored off. And it's a good reason for that. Yeah? So at that time, people were working on simple data sets and simple models. Yeah? And so in some sense, the models were even simpler than the data because there was no really kind of, computing, meant that people had to apply these ideas of conjugate priors. So you couldn't there's no Markov chain Monte Carlo around to help you, no kind of very, very good stochastic optimization techniques, no variational Bayes, all of these approximate methods. And so people spent a lot of time worrying about, well, if I have to assume this kind of what's called a conjugate prior in order to do the computation, what are the implications of that? And then what happened in the kind of the early 2000s is there's this kind of revolution in computational methods that came around through Markov chain Monte Carlo. So suddenly there was these computational tools came into the environment that said, well, you're not restricted to this specific class of priors which you can work with. You can go out and you can develop hierarchical models, and you can develop non-parametric priors, and there's a computational machinery that will allow you to do that. Yeah? And so the field really kind of took off, Bayesian statistics really took off, and there was much less concern about this issue of robustness because the models were very rich. Yeah, so in some sense, the models then outpaced the data. Initially, you had the data and the models were lagging behind. People worried about robustness. In comes MCMC, and then the models go past the data. Yeah, because you can fit hierarchies on hierarchies, and all of this was fine. Well, now we're in a world where it's like, return of the data. Yeah? So now the data's coming back, and coming back so fast. Yeah, in this kind of world of cheap measurement, cheap data capture, cheap storage. Yeah, that the data sets have now gone straight past the models where we can realistically use what we would normally take off the shelf, hierarchical Bayes, MCMC will just not work in these approaches. So now the data's outpaced the methods. So I think, we're going to see a reappraisal of robustness. We really need to worry. And this is because, if you chart the literature, the recent literature, there's been an explosion in approximate methods. So I think earlier on this week, you've certainly would have covered INLA, I know, because Harvard was here, and you've covered ABC because Christian was here, and I guess for many of you, will also be familiar with things like variational Bayes, Markov chain Monte Carlo approaches. Maybe some of you will know packed Bayesian approaches. The issue here is that they're approximate by design. Yeah, so they're not even starting off from the assumption that you're modeling the truth. It's like, look, we can't adopt anything that's close to the truth. We're going to adopt an approximate model. And so the question is, what are the consequences of these approximations? Yeah? How robust is inference to inherit model misspecification? If interest is in the science, i.e., what is the effect of this drug on this treatment? What does, how can I just plug this object in to my learning? Yeah? What does it represent? There's another issue. So this is one major issue that's hitting Bayesians. There's the other one, of course, that underlies Bayesian inference, which is the big elephant, the word that should never be spoken as a Bayesian, which is the elephant in the room, is that for Bayesians is that formally Bayesian statistics is conditional on the model being true. Yeah, and this is called M closed. Yeah, the M closed, the M stands for model. The closed means within the probability space that I'm defining under my prior, with probability 1, as in I would bet my life or your life, or well, I bet your life, but I would bet somebody who I care about, life, that I have the true model, the true data generating mechanism, the true likelihood here is contained under the support of my prior. Yeah, that's the kind of like the assumption number one, and you need that for all of the Bayesian learning, all of the updating to then carry forward. Yeah, if you want to kind of crank the Bayesian handle and for it to mean something, yeah, then you're making this assumption. Yeah, when I say the model being true, I mean the true model is contained under the support of the prior. You say, well, I don't believe that. Well, then what is the interpretation of P of theta? Yeah, what does the prior P of theta represent? It represents your prior beliefs that the true unknown value of theta takes that particular realization. Yeah? So it's linked to a kind of formally, if you want to update using Bayesian statistics, you have to assume you have a true likelihood. Yeah? And so you have to assume that the model is true. And the other kind of statement, if this were kind of a few statements I would like you to take away with you. This one has stayed with me since I was a PhD student. When I was studying Bayesian statistics, is that all of Bayesian statistics is model-based. It's a very kind of simple statement, but it's a really nice, concise. So everything that you want to do, like testing, a prediction, model comparison, model criticism, everything is model-based. So it's not like in classical statistics. If you want to test, you do a t-test, you set up some, a test statistic, and then you derive its distribution under the null. Yeah, none of that happens in Bayesian statistics. Bayesian statistics, and one of the really attractive parts of it, is that it's all about modeling data. Yeah, everything you want to do is model-based, but everything that's model-based is conditional on that being true. So then the answers that you get out, what do they mean? So as I said, robustness is not new in Bayesian statistics. There's a rich literature. There's excellent reviews. As I said, these are in the notes at the end. These 2 review articles by Berger are well worth reading. It's principally around the traditional was to look at robustness in the prior, assuming the likelihood is known. Yeah? And there's kind of good reasons for that. Like if you alter your likelihood, you also got to alter your prior as well, yeah? Because the prior is with respect to the likelihood. If I change the sampling distribution, the meaning of the prior changes. So you're always faced with, if you're going to change your model, you're always faced with having to change your prior. So a lot of work kind of went into that. I've said all of this, it's feel kind of tailored off, really because computation just initially outpaced data, and now, we had the return of the data, and the data's gone past the methods. Yeah. And so I think, as I said, this merits a kind of reappraisal of Bayesian robustness. Okay, so that's rather kind of long kind of scene set in. Let's begin with some examples. And what I want to do is take you through a very kind of simple kind of toy example of what I mean by a robust likelihood, a sampling distribution. Yeah. Okay, so it's well known, I think you know, if you were to apply a linear model. So suppose you've got a continuous, this would be a regression problem. Yeah, I have some continuous response variable y, that's the thing I'm interested in predicting. Yeah, and I believe that it's linear. Okay, x could be a dictionary. Yeah, so of course this is quite general. Could be a set of nonlinear basis functions of which we're combining in some linear fashion at the top end. Yeah, so what we know is that if you fit the normal model, so if I fit this model with these coefficients or these weights beta using like sum of squares or using Gaussian likelihood, we know that you're sensitive to outliers. If you get an unusual observation in your data, your model can just turn its nose and just track that. Yeah, we say that has high leverage. Okay, and so how do formally people adjust for that? Well, one way of saying it is that if this noise process is too light-tailed, yeah. So in other words, if you get tracked out by an outlier observation, we can robustify, assume it, like change your likelihood from a normal to a student. Yeah, we all know that the student has heavier tails. Yeah. So if I change my error process to now a student, then when I come to try and infer or learn about the values of beta in order to say make prediction, I'm not going to get tainted or pulled out by an outlier observation. So if you were non-Bayesian, you would reach for an estimating set of equations like M estimation or Huber likelihood to fit these models. You know, Bayesian analysis is more complicated because you have to define a joint distribution. If you're doing probabilistic modeling, you need to define a joint density. And this is why robustness is particularly kind of important. Okay, so here was the question I put at the beginning of the talk. So in classical statistics, you talk about robustness to outliers. You don't want to get affected by an unusual observation in a particular way. Yeah. So in Bayesian statistics, people talk about being outlier prone. Yeah. And outlier prone is a good thing. Yeah. You might say, well, you're prone to outliers. That doesn't sound like a good thing. Yeah, but when you think about it, if you think about the fact that Bayesian models are generative, yeah, you want an outlier-prone sampling distribution. That is, you want a sampling distribution or a likelihood that has a reasonable probability of generating you an outlier. Yeah. Because if your forward generative model has very low probability of generating an outlier, when it sees an outlier, it says, wow, that's unusual. I must have kind of, you know, says, anthropomorphizing my model. So one way of an analogy is the model thinks, you know, oh, that, you know, it's unusual to generate a data like that, and therefore I need to shift, yeah, to change the track list. And like robust analysis really dates back to the work of Dave Finetti, who is one of the founders of, or probably, you know, one of the main founders of modern Bayesian statistics, and pointed out this idea of, you know, needing to accommodate outlier-prone distributions, and mentioned really rather than say discarding outliers, trying to detect them and discard them, we should be probabilistically downweighting them in a formal Bayesian framework. Okay, so Dave Finetti considered the following sampling model. Yeah? So suppose you have a very simple model. We're going to say that the data here is going to come from a normal distribution. It's got some mean mu. But now, like if we go back up here, here we assume that y comes from a normal distribution with mean x beta. I can wrap the x beta into this central location here. And then just has an error term which is sigma squared I. Here, I'm going to give every observation. So suppose I'm predicting on you as a group. Every one of you has your own unique, individual sample, extra error term. Yeah? So I'm going to give you your own variance parameter. And I'm going to build that into a hierarchy in that I'm going to assume a distribution for those individual extra components of variation. And for sake of argument, I'm going to adopt an inverse gamma distribution. So this is an appropriate distribution. It has a probability measure on the positive reals. It's on the correct space. And so, why might this be a plausible model? Well, it's like each observation is taken from an instrument with normal error, but every time there's an additional, there was a random collection of instruments with different precisions. And the distribution of precisions are being indicated, i.e. there's some additional level of uncertainty that we're not accommodating for in our original model. Okay. So what does this look like? So I can define this kind of system or define this model. I now have a model for the y's and then an individual variance component. Clearly, I could set this as a very trivial computer task. What happens is I draw the y's, the lambda i's from inverse gamma, and then I'm going to draw the y's from a normal with some fixed sigma squared, but every yi given its partner lambda I is going to be drawn from that distribution. I'm just going to show you some plots of what this does. For various values of nu, which is in this inverse gamma, nu over 2, nu over 2. Okay. And it's just for sake of argument, I'm going to set mu 0 and sigma squared 1. So we're just going to look at what does this thing do? Yeah, if I start generating. Some of you have a show of hands. Does anybody know show of hands of people know what this will do on the y's? Okay, that's good. Yeah. So what's going to happen? So I'm going to generate from an inverse gamma with parameter 1, 1, then a different set of results with parameter 5, 5, and then a different set of results with 50, 50. Yeah? Because this is going into the inverse gamma here. Okay. So here is for nu equals 2. And here's a scatter plot of the yi's. That's the thing that I observe. Yeah, say. So this would be your height. Well, not your heights because they're negative, but say how much money you have in your bank account. Yeah? So this chap here, is that? No, I don't know. So what I've done is I've first of all generated a lambda I for each individual. I pick a person. Yeah, I'm going to generate you your variance component, which is your lambda I. Yeah, and they're going to put that into the normal distribution and generate you from a normal 0 with the lambda I. Okay, and because there's variation in the lambda i's, yeah, there's additional variation in the yi's. Okay, if the yi's were drawn from normal 0 sigma squared, then the lambda i's would just be 1. Yeah, and I think what you can see, although it's a bit hard, is of course there's dependence. If the lambda I is very large, then I'm suddenly generating from a normal with a very high variance. Okay, so you're more likely to be out in the tails. Yeah, there's more probability measure in the tails of in the tails of that distribution. And I generate, I think, about 10,000 samples from this very just simple model. Draw the lambda i's, draw the yi's, and it looks like this. The histogram is not the best way of looking at this data, but what you can see is that it's kind of symmetric. Well, yeah, you'd expect that because the underlying sampling distribution is just normal, centered at 0, but with just the variance it's kind of flapping around as you draw the lambdas. Yeah? But of course what you see is that relative to a standard normal, you've got very large outlier observations, down to like -10 and +10. Observations that you would never expect to see if you were just generating from a standard normal. Okay, so that was with nu equals 2. Yeah? So what happens if we up it now? We up it to 10. Yeah? So what we know for the inverse gamma is that the higher the values of the parameters, yeah, the more concentrated the distribution will head towards around 1, in fact. So if I generate from an inverse gamma with parameter 1,000, 1,000, most of those samples are going to be will be very close to being 1. So here I'm generating an inverse gamma 5, 5. Well, again, we see heterogeneity. The scale has changed here. So previously we were on the scale of 100 to 0. Now we're on the scale of just 0 to 5. So what we can see is that, again, there are a few large variance observations. And there is, of course, dependence. Yeah? That the higher the value of lambda, the greater the chance that you have of being out in the tails, because I'm generating from a normal with that particular variance. And so again, we can see the distribution looks symmetric. This is just the projection. It's the marginal distribution. Yeah, it's just the projection of these points onto the y-axis. So that's with 10, 10. We can see there's less weight out in the tails, but there's still some observations that are large, -6 up to +6. And then we go up to 100. Now things start to look stable. You know, the lambdas are actually concentrating around 1. You know, and in the limit, what's going to happen? If all the lambdas are 1, you're back to a normal. Yeah? So it's like adding a bit of noise. There's a bit of extra noise that's coming about from this heterogeneity. So I think we could see intuitively that in the limit, if I go up to an inverse gamma, a trillion, yeah, then almost all of the lambdas are going to be near 1. And this thing's going to be pretty close to being a normal. Yeah? But is there a way that we can actually kind of quantify this? Formally, do we know what's happening here? Okay, and so this is just to show you a QQ plot, a quantile plot of the distribution of the observations by generating under a nu of 10 and a nu of 100. Okay, so here's the nu 10 and here's the nu 100, and you can see that the nu 10 has heavier tails. Because if I look at the smallest observation under from generating with 100, that's at like just say -3.7, and that has a value of -5 on here. So this kind of characteristic kind of slanted S shows that there's heavier tails. Okay. Well, you know, Dave Finetti knew what was happening here. The reason why you chose the inverse gamma was for a good reason. And the fact is that the reason is we know that it's something called a conjugate prior. Yeah? So this variance component here is called a conjugate prior, which means that actually, when you look at the marginal distribution of y, we're going to integrate the normal distribution, which contains the value lambda, with respect to this prior. Yeah? And it's kind of, well, relatively well known that this is the conjugate prior, which means that this has a closed form solution, which formally means that those yi's, when I was showing you these histograms here, these are student distributions. Yeah? It's a really nice, I think it's a nice way of thinking about the student distribution. Yeah? So what does a student distribution equate to? It equates to kind of additional, extra kind of components of variation. It's as if every individual had some extra heteroscedasticity, some extra kind of noise process going on. And the level of the noise process, this degree of freedom nu, is precisely the parameter that enters into that inverse Gaussian, gamma, inverse gamma. So when we say, oh, let's adopt a student distribution for the sampling distribution in my regression, we're not in some sense plucking that out of thin air. Yeah, there's a kind of an underlying generative model for it. Yeah, and that generative model is that there's some kind of additional parts of variation that our model has kind of missed out on. And if we're prepared to kind of accept that those could be modeled well by an inverse gamma, then we can then justify the student distribution. Okay. This as well is why we can see that if the nu heads off to infinity, yeah, then those inverse gammas are all going to be generated at 1, and we know that you're going to get back to a normal density. So the robust student density naturally arises by thinking about this additional heterogeneity. Okay, can we go further? So that's, we've looked at this in terms of, we've got a regression problem. You know, I'm worried about the normal distribution or my particular sampling distribution. I can kind of persuade you that maybe the student distribution is quite a nice way forward to go. What about arbitrary, likelihoods? Or are there more systematic ways we can look at this? And there's one way of, a good, nice way of characterizing the influence of data on your probability model. Again, all of this is assuming that you're adopting a probability model, a probabilistic approach. And that's by the use of something called score functions. So score functions provide a good way to examine model sensitivity to observations. So we're going to be in this Bayesian world. Yeah, we've got our current beliefs about parameters are summarized by this prior. So we've got the prior beliefs on the parameters, and we're going to look at the influence of a new observation drawn from the likelihood on beliefs about a particular component, theta j. So I'm going to choose one parameter in my model. Yeah, I've got a joint posterior distribution over all of the parameters. I've got one particular parameter, say, of interest, theta j, or what I'm currently looking at, theta j. And what I want to know is, you know, how influential could an observation be about this value? And to do that, we can look at the posterior, something called the posterior score function. So what is this? This is for the jth component, it's the jth partial derivative of the log probability, of the log posterior. Okay? And because we're taking logs, of course, the partial derivative of the log posterior just breaks down into an additive function of the partial derivative under the prior, the log prior, plus the partial derivative under the log likelihood. Okay. And it's this term that I'm going to be concerned with here. Like, you know, what is the influence? I want to know what's the influence of an observation on my the posterior distribution. You know, I'm concerned maybe that if an observation goes, you know, is an outlier, it could really shift my whole kind of model across. And the dependence of the posterior score function on the data is through something, well, it's called the efficient score. It's known as the efficient score. So it's the gradient of the log likelihood, yeah, evaluated at theta, written as a function of x. You need to get your head around what's the likelihood function. Yeah? So the likelihood function, yeah, thinks about the likelihood of theta, yeah, for a fixed value of x. Okay. And so this is just the log likelihood function there. Okay, so, well, clearly, again, through taking logs, the derivative of the log posterior is just the sum of the partial derivatives for each observation. Yeah, because we have conditional independence assumed here. So this highlights the additive contribution under a conditional independence model of the ith observation to the jth partial derivative of the log likelihood function evaluated. It's a bit of a mouthful, that, isn't it? So what it tells me is, it says, you know, if I think of all of you as data points, if I take one of you, yeah, and I shift you around, yeah, what is the influence that you have on the gradient of the posterior distribution for any value of theta? I choose a value of theta, and then I wiggle you, and then I can say, well, how does the, you know, what happens to the gradient of theta? And why is that thing of interest? Well, because we know, of course, at the posterior mode, yeah, or at the map estimate, at the most probable value of theta, we know, of course, that those derivatives will sum to 0. Yeah, because you're at a maxima. So we know that at a maxima, yeah, we know that these score functions, the sum of the score functions will equal 0. So if we want to choose a point in theta space to examine influence, one good position to look at might be the mode. Yeah? How does the mode shift around? Or what happens to the mode as observations move? You know, if I shook my data a little bit, I jiggled my data, what would happen to the mode? Would it just start shifting all over the place, or would it be stable? Okay. And one way you can look at that, about how much the mode would shift, is by noting, well, what I know is that the mode, the sum of these scores has to be equal to 0. So intuitively, if one of those score functions is large, then it will influence the map as, so to speak, the map has to move, yeah? In order to position, of course, it doesn't actually move. But, you can think of it as that the map estimate has to move in order that of course, that it remains a mode, yeah? It remains a maxima. Okay. And the map is really the balancing point of the score function realizations. Okay, so at the mode, we know those score functions have to sum to 0. So by examining the form of those score functions for different sampling distributions, we can see how a kind of outlier-prone a distribution is. And remember, like, outlier-prone is a good thing here. Yeah? That's what we want. We want a model that can generate us outliers. Because then if we see one, we're not going to get unduly influenced by them. Okay, so again, let's have a look at, what are these score functions? They're like they're derivatives of log likelihoods, these log probabilities. What do they look like for some standard models? Okay, so consider a standardized observation Z. But by that I mean I'm going to take my original data point and I'm going to subtract off the mean and I'm going to divide it by the standard deviation. Okay, so it's just going to help me for illustration. Then we can look at the relative influence on, say, for a Gaussian, the central location and the variance. Yeah, and I'm going to look at what do these score functions look like for both the Gaussian and for the student distributions. Okay, and so to do that, I just have to differentiate the log likelihood function, or the log normal. Well, not the log normal. The log of the normal. Yeah? The normal logged. Yeah? There's a difference, because the log normal is a distribution. So if I take my my normal distribution, the location efficient score looks like this. So the derivative of the mean, yeah, for a standardized observation is just Z, the value of the standardized effect divided by sigma. Okay, so that's just linear in Z. And we know, of course, you could see this, that in order to estimate the mean, yeah, that's like the mode, it's the map estimate, yeah. We know that the sum of these score functions has to be equal to 0, which kind of makes sense, yeah. It's going to be the arithmetic mean. Yeah, the sum of the z's, because sigma's fixed, the sum of the z's have to be equal to 0 at the map, at the mode. What's the effect of an observation on the variance parameter? So again, we look at the partial derivative of the variance component, or the standard deviation, and we get this form that's quadratic in Z. Yeah? So we see, well, actually, so now this observation has a quadratic influence on the variance. Yeah? The larger the observation is, the greater the pull. And again, we know that the sum of these scores has to be equal to 0 at your map estimate of sigma. So we can see there's kind of quadratic influence coming through on the variance. So what do they look like? Oh, I don't know if it's come. Well, the lines have come out, but this one, have a look at, is it just my eyes or? Yeah, no, this one is clear. So have a look on this side here, yeah? So what do we see? We see, well, the efficient score function for the central location is just linear, yeah, so as we suspected for on estimating the mean, yeah, and it's quadratic in terms of estimating the variance. And in particular, look at here. Here's 0. Yeah, and so there's some negative components here, parts here to this function, and some positive parts. And remember I said that the sum has to equal 0. Yeah, the crossing point here is at the standard deviation. Yeah, if you think, I mean, you need to think it's a Sunday morning as well, so you need to think about that a little bit, which says that at the map estimate, assuming a flat prior, the map estimate, your best estimate for the variance component, it's the balance between the sum of these negative observations, which lie within one standard deviation, yeah, and the sum of the things outside of one standard deviation, yeah, and those things have to balance. You need to set the standard deviation, the width of the things that are inside, the sum of those equals the things that are outside. Yeah? So you can see how the standard deviation is set, kind of trading off those two things. What happens if I change the underlying standard deviation of the normal? Well, we can just see that it just changes the overall shape. I'm sorry about the colour here is a bit diluted. But the main thing to note is the influence on the location goes like 1 over sigma. Yeah? In terms of the influence of an observation. And for observations, in terms of the variance component, for observations less than sigma, so for those observations which lie within one standard deviation of the mean, they have a negative effect on the score for estimating the variance component, and for those out, they have a positive effect. And trying to find, your optimal value balances off those two things. So what happens for the student? Yeah? So we talked about before, where we said, the student kind of looks like it's robust. It's got this notion of an extra level of heteroscedasticity. What does it look like? Well, what do the score functions look like? You have the following form. If I differentiate the central location of a student distribution with respect to the observation, it looks something like this. It's got not a particularly kind of intuitive form, but you start to see something. You say, well, look, I've got a z over a z squared here. So I've got z squared on the denominator and a z on the numerator. So that's looking promising, yeah? And then the scale efficient score, you've got these two things that are ratios of z squares with some kind of constants, the degrees of freedom of the student in there. Okay. So it's hard to just kind of picture those, it's hard for me to visualize, you're maybe better than me at that. But just kind of plotting those out, it's very kind of interesting to compare them to the normal. Yeah? And again, it's a nice thing that this, people often use student distributions. We use a student 4 or a student 8. But often people don't have a very, like if you are, the interpretation of a student distribution, with the degrees of freedom. And I think it's quite nice to kind of score functions give meaning, yeah, in terms of like this robustness and in terms of the degrees of freedom. So it's pretty weak as in the picture here, but what you can see compared with the normal, which has unbounded influence on the estimate of the mean, yeah? So if I have an observation here, he starts off at 0 and starts to track out, this observation starts to head out in here, then we know that the score, the total score has to be equal to 0, yeah, at the mode. So the further that this observation heads off out into Reykjavik, yeah, the more the mode is going to have to track it. Yeah, it's going to follow it. Yeah, the mean of the data, of course, is just going to get tracked linearly by that one observation. It's going to have leverage 1 over n. Okay, and moreover, if I'm trying to estimate the standard deviation, yeah, as an observation heads off that way, its influence becomes quadratic in terms of estimating the standard deviation. Well, what happens for the student? Well, this has a much kind of nicer property. Initially, as I move away from 0, I get this kind of linear contribution. Yeah, so it's an observation. It's almost like, again, I'm trying to put in human characteristics on my models. Yeah, but like initially, if the model thinks, oh yeah, this is an inlier. Yeah, it looks like part of the mass of the data. You have a contribution 1 over n. Yeah, so you have a linear contribution to estimating the mean, the central location of the student, as the observation moves away from 0. But then there's this turning point. And as the data gets further and further away, yeah, for the Gaussian, you'll just keep tracking it. It's linear, yeah? But in comparison for the student distribution, the influence tails off. So the further you go away, the less influence you have relatively on the estimate of the mean. Remember that the map estimate under a flat prior will lie when the sum of all of these score functions for each individual observation equals 0. Okay, so we can see that it has this kind of turning point and it has an asymptotic decay. Yeah, and in fact, for large z, you can see, I mean, this is just trivial. You look at this function here. What happens for large z? You have a constant times z over something which is negligible because z's getting really big. Yeah, so I can just cancel the z from top and bottom. So this thing tends to this as z goes to infinity. So we can see this decrease in influence on the central estimate of the central location. What happens to the variance? Well, again, around 0, estimating the variance, this thing looks quadratic. Yeah? So around 0, it looks like it has the same influence on the scale as it does for the Gaussian. But here we have bounded influence on the variance. Yeah? And in fact, this asymptotes, whereas the variance of the normal just goes quadratic and increases, unbounded. The variance or the score function for the student on the variance asymptotes to for if sigma is 1 to the degrees of freedom to the student. Yeah. So one interpretation for say what's the meaning of a degree, or one consequence of setting say a degree of freedom of say 4. Yeah, is that you bound the influence of an observation under the student, yeah, in terms of its score for the variance to be 4. Yeah, so as the data moves out, you have bounded contribution on the estimate of the variance, and you have a decrease in relative contribution in terms of estimating the mean. And so this is kind of like formally why we would say, the student distribution is robust. Yeah. And it's kind of a rule of thumb that if you fit things using sums of squares or normal distributions, you just have to worry. Yeah. You really have to make sure that you do your diagnostics well after. Yeah. So shake your data, bootstrap your data, look at the leverage of individual observations, just to make sure you're not being kind of dragged out. In some sense, you're better off building that in the model, especially when we're in these kind of very, very large kind of big data problems. It used to be that fitting like student distributions was problematic because of, computate used to be. That's like, a different world 20 years ago. Now kind of modern kind of computing, stochastic optimization allows us kind of routine application of these kind of likelihoods. And so these are just 2 slides comparing overlaid a student 4 with a Gaussian, and there we can see again these things we talked about. The asymptotic decay of the influence on the central location and the bounded influence on the variance component. I think it's now is a good time for us to break. So what I want to do after you've all earned yourself, more than earned yourself, coffee. So what I'd like to do after the break, I'm going to start to go through. So what we've covered so far is really the motivation for robust inference. Why do we have to worry about assumptions, especially in probabilistic models? I've talked you through a couple of simple scenarios for robust likelihoods, sampling distributions, and using things like students rather than Gaussians. And so after the break, what I will do in the next lecture is talk you through formal methods for looking at robustness to prior assumptions. And so the way we're heading in here is this idea as a model, as a point in a probability space for which we're going to define a class of distributions or a ball of distributions around that point, and we're going to look at robustness issues within that ball. Okay, thank you. See you in a bit.